Don't let that dot matrix printer fool you. That machine is a beast. So what is it? It's a liquid scintillation counter. It lets us measure the radioactivity of samples. I use it for my kinase assays, so when I'm studying phosphorylation, but you can also use it for things like studying how molecules are made by tracking the radio labeled isotopes. We'll get into this and where they go, as well as studying like drug metabolism, and so how drugs are like taken in and broken down by the body, as well as things like taking wipes from surfaces and testing to see if they're radioactive. So basically we have some sort of radioactive sample. And so it's what it means by radioactive is that it's undergo this decay process I'll tell you about, where it's going to let off energy. So if we can measure this energy, we can measure the amount of radioactivity. In order to measure this energy, what we're going to do is we're going to use a scintillation cocktail containing these molecules that are going to absorb that energy and give it back as light. And then we're going to stick this into a machine, and this machine is going to then take that light and convert it into using photomultiplier tubes. It's going to convert it into this electrical pulse, and then the computer can measure this and then calculate how much radioactivity was in your sample. And so you can then get ideas about what's going on at the molecular level. And the really great thing about using radioisotopic labeling, which we'll talk about, is basically that when you use a radioactive version of an atom, of an element, so like I use P32, so radioactive phosphorus, you can also use like radioactive carbon or radioactive hydrogen, it's going to act like identically to the other to the like normal non-radioactive versions of it. So the other molecules aren't going to realize that something's weird, like they would if you had some big fluorophore or something conjugated, so like stuck onto your molecule. So it's a really helpful way to study things in like their native environment using this radioactivity counting with scintillation. So let's talk about how liquid scintillation counting works.
So I'll get into the details of how it works and the molecular basis and all the stuff about what radioactivity even is and why we're trying to measure it. But first, I just wanted to give you a look at it because I think it's really cool. So this is probably the last selfie I'll be taking with this scintillation counter before I move on to my postdoc at UCSF. And I don't know if I'm going to be using a scintillation counter there, but I've had many a great day with this scintillation counter. So there are, I feel like in science, there's either equipment either lasts forever without ever having an issue, or it is like works for 2 days and then breaks, and then works for 2 days and then breaks, or then it goes obsolete. But sometimes equipment like this, it's just very, very durable. And so this machine might look really old, but it is still really, really powerful and useful. There are a couple bad things about this particular machine. One is that the computer is not like, it can't save files or anything. And so the only print reading you have is like on the screen, and the only permanent record you have is this printout on this dot matrix paper and printer, which I'm like terrified that it was going to run out of paper. I have to try to refeed it, or it was going to break or something, because this is like your only readout. But thankfully it lasted me for all of the experiments that I had to do. And it isn't quite as old as it thinks it is. So if we were to zoom in onto the date, we can see that yesterday it thought it was 1922, March 10th, 1922. Apparently it has a Y2K problem where it can't recognize, it can't go past into the new millennium date-wise. But anyway, let's take a look inside. So we have our samples, and we put our samples into these little scintillation vials. And then these are going to go into these racks that are going to go into the machine. So it actually has these, it uses these like punch cardy type things that you put on behind the rack to tell it what to do. And you can see that it's going to move it. It's abducted one of the samples to go measure it, like a little UFO abduction. So if we watch that again, you can see here it's going to put back the sample that it did before. Then it moves over, and then it takes the next one. So it's really, really cool. So it's taking it into this chamber where it doesn't have to worry about picking up the radioactivity from the other samples. So you measure them one at a time. And then hopefully the results are good. And then these results are going to be read out on this computer and then printed out. So if you were to, what you see on the computer screen when it's working, it'll kind of like, you tell it how long you want it to collect the sample for, or like measure for. And so you do like, I think I have it set for 15 seconds, 30 seconds, I can't remember. It feels like ages. But you can see that the signal is kind of moving all around. And then it is going to kind of finalize on the value, and then it is going to give you a readout, and it's going to print that and go on the screen and then move on to the next sample. So sometimes when there's been like really critical experiments, like you're just waiting so anxiously, like watching the screen and like waiting, and then because you have to check and then wait for your negative controls and make sure everything's all good. But when it's all good, it's a very happy day. So now that we've seen like what it looks like, let's talk about like what it would look like at the very, very molecular level. So what's happening is we're measuring radioactivity. And so the basic of radioactivity is that we have versions of molecules that act like they're normal, but they give off this radioactive energy. So molecules are made up of atoms, and these atoms are made up of smaller parts, subatomic particles. So they have in their nucleus, the central nucleus, they have positively charged protons and negatively charged. So in this central nucleus, they have positively charged protons and neutral neutrons, and then they have this cloud of electrons hanging around them. So different elements, so nitrogen, carbon, hydrogen, etc., are defined by the number of protons that they have. But the number of electrons and the number of neutrons can vary. If you change the number of electrons, now you're going to change the charge. So this is how we can get like anions and cations, so charged molecules, if they have an imbalance of electrons and protons, because they're equal but oppositely charged. You can also, if you change the number of neutrons, well, these were neutral, so they're not going to affect the charge, but they might affect the stability. If you try, the neutrons are really important for helping kind of glue the nucleus together. So you have all these positively charged protons and opposite charges attract. So the neutrons are really helping hold all of this together. If you have too few or too many neutrons, now you're going to have an unstable nucleus. And if you have one of these unstable nuclei, then you can undergo radioactive decay. And there's a few different types of radioactive decay. And the type that I'm working with, that I measure from this P32, this radioactive phosphorus, is this beta decay. There's just different types of decay that allow the nucleus to kind of rearrange itself and get happy with its current situation, because it gets really uncomfy if it has too many or too few neutrons. And so when it gets unhappy, it's going to let off this radiation. And so these radioactive particles, they're high energy. And so if we can then detect this energy, that would give us a way to detect how much of the radioactive thing there was. And this is the idea with liquid scintillation counting, that the radioactive decay particles, the energy from them is going to be converted into detectable light. And then this detectable light is going to be converted into an electrical signal that can be measured. So in our sample, we have something that's radioactive. And then in order to convert it into this detectable light, we're going to put it in a scintillation cocktail. So this cocktail is a couple things. It has a solvent, and it's going to like help dissolve your sample, and it's going to help relay the energy to these parts that are going to do the light conversion, these like scintillators or fluors. These are going to absorb the energy from the solvents. The solvent's going to kind of help pass it off. It could go directly to the scintillator, but you have a lot more solvent molecules than you have these molecules. And so the solvent is kind of helping act as an in-between. it can pass it on to the scintillator or the floor. And what this can do is then it can give off light. So there's not always a primary or a secondary scintillator. But there often is. The secondary scintillator it helps like shift the wavelength into a better detectable light, at least in the older ones, and apparently it has better sensitivity and stuff. But the basic idea is you have this energy being passed off and ultimately given off as light. Then this light is going to go into this liquid scintillation counter. There's these photomultiplier tubes. Don't ask me how they work. I'm not like a physics person, but they're going to amplify the signal and convert it into an electrical pulse. And then the pulse can be measured and it can be converted to an amount of radioactivity. What's really cool is that different elements have like different decay energies. Like in their decay particles, they have different energies. So you can actually measure, like with different channels, you can measure different radioactive isotopes. So different versions, we call like isotopes when they're like nuclear isotopes when they're have different numbers of neutrons. We call them radioactive isotopes if those are unstable. So they're not always unstable, but the radioactive ones we call like radioactive isotopes or radioisotopes. And they have different energies that they're going to give off. And so you can actually measure like different radioisotopes in the same sample. And this is really cool because being able to radio label molecules is a really great way to kind of track how things are made, how things are degraded, where things are going, because you're changing out atoms without the other molecules around it kind of recognizing that anything's going on. In terms of what these actual molecules are inside of the scintillation cocktail, it's going to vary depending on what type of sample you start with. And so you can start with like solid samples. So when I do it, I'm start like spotting a liquid sample onto one of these filter papers and putting that in. You can also have like little wipes that you put in if you do like a surface wipe. There are various different ways. You can have like a scraping from something, lots of different ways. And because those things that you're putting in there will have different properties, then you can use a scintillation cocktail that is better suited for it. One place where this comes into play is if you have a liquid sample. And this scintillation cocktail is really oily. This solvent is like typically an organic solvent. So it's something you can kind of think of it as like oily kind of, and oil and water don't mix well. And so the scintillation cocktails often have some sort of surfactant that is kind of like a soap detergent type of thing that's going to help it so that you don't just have like your stuff is just surrounded by the thing and then all your stuff is kind of like clumped in the middle. You want your stuff to be well dispersed. You want like the radioactivity to be well dispersed throughout this liquid cocktail, and so the surfactant would help with that. Then you also have the like scintillators or the floors, and so you might have just a primary, you might have a primary and a secondary. They differ, and there's different details on all of that stuff in other places, and I'll direct you to a good link. But one thing that both the solvent and the scintillators tend to have in common is that they have a lot of aromatic rings. So basically, aromatic rings are when you have electrons shared throughout a ring. So when atoms are linking up to form molecules, they do so by sharing pairs of electrons. And when they share this in kind of this communal way around a ring, we call it aromatic. And the important thing here is that when energy is being absorbed by these molecules, what's happening is that the energy is being used to like excite electrons. So electrons can like live in different energy levels. And if they get more energy, they can kind of get promoted to a higher energy level, but they can't stay there for very long. And so then they fall back. And they can fall back and give off that energy in different ways. And so if they give it off as light, then we call it like luminescence. And if they absorb the energy from light, then we call it fluorescence. And if it was from a chemical reaction, it's like chemiluminescence and stuff. But the important thing here is that the ability to absorb this energy is going to depend on whether that energy matches the amount needed to excite the electron to the higher level, because it has to be like perfect amounts to excite it. And so the distance between these is going to be determined by the molecular makeup. And when you have an aromatic molecule, when you have like conjugation, where you have this kind of like shared electrons, then you have this, it makes it easier for electrons to absorb light in front of the energies that are useful to us, basically. And so you'll see a lot of these molecules are going to have these like aromatic rings, this conjugation. And this is going to allow them to absorb the energy and ultimately give it off as this light that's detected by this scintillation counter. You might have be thinking like, people actually still use radioactivity? And yes, we use it all the time, especially so when I'm working with like RNA, I radio label the ends of the RNA. And this is really helpful, and it beats putting on like a big fluorophore, a big tag on it that's going to give off light or make it detectable some other way, but then could interfere with other processes. Scintillation counting is really great because it is super duper sensitive, and there are a lot of different types of samples that can be analyzed with it, and you can analyze different types of radioactivity. It is limited to the types though, so when I say like can measure how radioactive samples are, it's really primarily with like beta decay and alpha decay. So if you have like this isn't being used to measure like super duper high energy radiation, but it's really great for measuring the types of molecules that we use in biochemistry, things like P32, C14, tritium, various things like that we can use to label molecules and track them. So in these specific reactions, I was doing this phosphorylation experiment. So studying this kinase, and so a kinase is something that adds phosphate groups to things. And so I study this protein kinase that adds phosphate groups to kinase. And what I can do is I can actually use radioactive ATP, which is a source of the phosphate group, so radioactive phosphate, and get that added onto my protein. And then what I'm putting in these scintillation vials is I actually spot it on these little filter papers. And then I wash off the pre-ATP, and then I put it into these scintillation vials with the scintillant. And so honestly, like one of the worst parts of the experiment is actually filling these tubes, because it's just a real like monotonous pain in the butt thing. Basically, I line up all these tubes in a little rack, and then I take a serological pipette, and I do 2 microliters, 2 microliters, 2 microliters, 2 microliters. It's going to depend on the size of your scintillation vials and stuff. So they come in different sizes. And then what I'm going to do is the part I really, really hate is capping them, because it's just like so tedious and like, yeah. But so the other part I really don't like is having our scintillation counter is actually across campus. And so I have to the other day I had to walk through the snow, but the happy results made it worth it because my kinase that I just purified is nice and active and happy. So that was good. But yeah, I put all my samples into this like box, and it's like carrying my little Santa sack is what my colleague calls it, across the campus to the scintillation counter. Just note that there are other ways that we can detect radiation as well. So this is like our Typhoon. What these are phosphor storage screens that we can use for like autoradiography. So basically these screens, what happens here is that because the radioactive stuff we can talk about like a half-life, which is the time that it takes for half of the sample to radioactive sample to like decay. But that's like on average. So this decay is just like this random process. And so you can't predict like exactly when it's going to happen. And you can't just say, okay, wait, everybody hold off. Okay, now decay. So instead, what you can do is you can take that decay and you can store it. So in these phosphor screens, these molecules can actually exist in this kind of like metastable state. So before I said how the electrons, when they absorb energy, then they fall down. Well, if you can get them to delay falling down and then direct when they fall down, then you can get a boost on your signal rather than trying to measure each little each little release event. So when I'm doing like it's just like an RNA urea page gel that I labeled these RNAs. I wanted to see if they were all intact and they all looked fine, no degradation, that sort of thing. So what I did was I ran them through a urea page gel, separate them by size, and then I actually put them on like a little piece of filter paper, wrapped them in saran wrap, and put them in this screen with the screen on top. And then what's going to happen is that when these radioactive particles are given off, they're going to get stored in the screen. And then when we put this in this Typhoon, this scanner machine, it's actually going to scan it with light. That's going to excite it and kind of get these molecules to give up their energy and give off light that's then detected. So this is another way that we can measure radioactivity.